Hey guys, this is part 3 of the series on energy-based models or EBMs. In this video, I will show how to perform a classification task using an EBM. I also show how logistic regression can be expressed within the EBM framework. To keep the concepts clear, I will discuss them to the breast cancer dataset. The following code downloads and stores the dataset in a data frame. Here, the columns are some properties of the breast tumors, and the last column is the class of the tumor, whether it is benign or malignant. For real data science work, one needs to better understand the columns of the dataset, but this level of info is enough for demonstrating how to perform classification using EBMs. So let's move on. In the next step, we split the columns. All the columns except the last one will be shown with capital X, and the last column, which is the class of the tumor, is shown with Y. In this dataset, one of the tumor classes is labeled 0 and the other is labeled 1. Since class labels are just a matter of convention, and since the energy form for the EBM formulation of logistic regression is much simpler if the classes are -1 and 1, we replace 0 with -1. Now let's remind ourselves that the goal is to train an EBM that, given the values of capital X, predicts the class of tumor or the Y variable, which is either -1 or 1. So we define the energy function as the negative product of the target and the weighted sum of the rest of the columns. In this equation, x1 to xk are the columns of the dataset, like tumor's mean radius and tumor's mean texture, and y is the last column, +1 for malignant and -1 for benign tumors. Also, we have a set of free theta parameters whose values will be set through the training process. To train this model, we need to remember part 1 of this course, where I explained that the most likely configuration of the system, which is the cancer cell in this example, has the lowest energy possible. So we need to define a loss function whose minimum corresponds to the minimum of the energy. For linear regression in part 2 of the series, we simply selected the energy itself as the loss function. For classification, we want to recover the loss of logistic regression. So we use the negative of the likelihood of the dataset, which is defined below. Note that when we replace the energy by its explicit form, this is exactly the loss function for a standard logistic regression. Also, note that as we lower the energy, the loss function decreases, which is what we expect in an EBM. To find the optimal values of the theta parameters, we need to simply minimize this loss function, which we will do using SciPy again. First, we implement the energy function and its derivatives with respect to the theta parameters. Then we set our initial guess for the theta parameters and then perform the minimization. Finally, we print out the first 5 values of the theta parameters. Now that we have the optimal values of theta, let's make some predictions in the EBM style. For a given row of the dataset, we will compute the energy of both of the tumor classes. That means we first insert the values of all the columns except the target column into the energy function. Now we are missing the value of y. First, we insert y equal to 1 and compute the energy. And after that, insert y equal to -1 into the energy function and compute the energy. The value of y that returns lower energy is our prediction. To see this in practice, in the following, we loop over all the rows of the dataset and show their energies for both values of y given the same capital X. Then we color code the true y value with red and the other y value with blue to see which one really gives the lowest energy and therefore is our prediction. We draw connecting lines to illustrate how the energy changes between the two possible classes for each given row of the dataset. As you can see, most of the red dots are on the lower side of the plot, which means the two y values have lower energies than their corresponding blue dots, indicating the wrong classes. The few red dots whose energies are larger than the corresponding blue dots are our misclassified samples. So now let's recap. To predict the tumor class of a row of the dataset, we inserted the values of all the columns that we specified as capital X into the following energy function. We also inserted the optimal values of the theta into the function. Next, we computed the energy once by substituting y equal to 1 and another time by inserting -1 for y. Then we computed the two energies and selected the y value that returned lower energy. But this is doing the prediction the hard way. There is actually a more efficient way to make the same prediction. Note that the lower energy will be achieved when y has the same sign as the weighted sum of the rest of the columns. So our prediction will be the following equation, which we have implemented in the following code and used to compute the accuracy of our EBM model. As you can see, the accuracy turns out to be 100%. Note that I trained and tested the model on the same dataset, which was to keep things simple. In a practical use case, we need to split the dataset to train and test. And this was it for part 3 of the EBM video series. If you want to exercise a bit more, try to perform a multi-class classification using EBMs. What would the energy function look like? Write your answers in the comment section below. And if you want to support me in creating more of these courses, the most effective way would be to introduce the courses to colleagues or friends who might find them useful. And one last thing, if you need my help to go through these materials and adjust them for your own work, I run a mentorship program where I personally guide people through physics-based AI models. If interested, book a short call to discuss your current level and your goal. The link is in the description. Take care and see you in the next video.